Okay, so good afternoon. Today's lecture is vector formulation in InSAR for land surface motion. So this is very important lecture because when we measure the land surface motion, so that is basically a three-dimensional motion. So suppose somewhere landslide is happening, so that mass movement is in the three-dimensional, like the mass is moving along the x direction, y direction, and the z direction also. So it becomes very important to understand how much motion is there along the x direction and how much along the y direction and how much is along the z direction. If this information is there, so then we can basically investigate the entire motion or the kinematics of that particular region. Okay. So to understand this means how we can calculate all three components of the deformation vector, or you can say the motion vector. So all these three components requires some coupling of the INSAR data sets. We have the data sets from the ascending pass as well as the descending pass. So if we are able to combine or couple both the outputs of the ascending as well as the descending passes, then by coupling we can calculate the x, y and the z components of the deformation vector. But in fact all three components are not possible from the two passes. So we can calculate only two components because of the practical limitations. So those two components we can categorize like horizontal vector as well as the vertical vector, or vertical component or the horizontal component. So that the horizontal component may be along the x direction and the vertical components may be in the z direction. So x direction in general I am saying here, but horizontal components on the earth surface may be along the east west direction or along the north south direction, and the vertical component is vertically upward or the vertically downward direction. So there are many examples, like if you are talking about the land subsidence, so that is the motion in the vertical plane only. So either land is going upward or going downward. So this is called the vertical displacement or the vertical motion, or you can say the vertical component of the motion vector. So this is the examples of the land subsidence. Similarly, in case of landslide, the motion may be in horizontal as well as the vertical directions. Same way for the plate tectonic movement or the glacier meltings or the tilting of the infrastructural buildings or the dams or the bridges. So means in all the examples of the deformation or the land deformation or the infrastructural deformation, we need to calculate the deformation components of the deformation vectors. Okay. So those things we will try to understand in this particular lecture. So how we can basically handle this real time of problem with the help of the ascending and the descending data sets. So in order to understand, we have to understand first what is a scalar and the what is a vector quantities. So scalar, these are the physical quantities which are having only the magnitude, and generally they are denoted by the simple letters like a, b, c or x, y, z, something like that. And there are other types of the quantities called the vector quantities. So vector quantities have both the things, both means magnitude as well as the direction. So the representation of the vector quantities may be like this: a, small a, b, c with arrow. So you can say the a vector, b vector, c vector, or you can represent by capital letters with arrows, or you can represent by the bold letters without arrows, small letters or the capital letters. So these are basically the notations to represent the vector quantity. Or in general, if you see, so vector is represented by a line, you can say, with one arrow like this. So vector is starting from here and ending over here. So these things you can write like starting point is P, ending point is Q. So the length from P to Q is called the magnitude of this vector, and the direction of arrow, this particular arrow is denoting basically the direction of this vector. So you can say this is a vector quantity which is having the magnitude as well as the direction of this particular vector. So this vector is denoted by a capital letter with arrow, or you can also represent like PQ then arrow, just like here it is mentioned. PQ means vector is starting from P ending at Q, and this is vector notation. So there are number of ways by which we can denote a vector quantity, but keep in mind vector quantities have the magnitude as well as the direction. Similarly, the another vector is shown here from Mn, so you can write like Mn vector, or you can say give another name like V vector. Okay, so this starting point is called the tail of this vector, and this arrow side is called the head of this vector. So tail and head, so you can say the distance between tail and head is called the magnitude, and the direction of this arrow is called the direction of the vector. Okay, so if you denote in terms of like this is basically a one dimensional vector, and if you are combining this vector, if you are putting in a 2D plane, then it is called the two dimensional vector, and if you are putting in the three dimensional frame, then it is called the three dimensional vector. So if it is two dimensional vector, so let us say this two dimensional means it has the two components, means one component along the x direction, another component along the y direction. So in general that two dimensional vector we can represent like vector A equal to a1 x cap plus a2 y cap. So x cap and y caps are the unit vectors along the x direction and the y direction respectively, and a1 is the length of the vector along the x direction, and a2 is the length of the vector along the y direction. So the overall length, if you want to calculate, then the length of vector A will be square root of a1 square plus a2 square. Okay, so and if you want to represent like a three dimensional vector, so it will be a1 x cap plus a2 y cap plus a3 y z cap. So z cap, y cap and x cap are the unit vectors, or you can say the direction along the x, y and z sides, and a1, a2, a3 are the magnitude of this vector along the x and y and z directions. So the magnitude, we can magnitude of this three dimensional vector is square root of a1 square plus a2 square plus a3 square, this one. And so this way we can these are the basic things about the vectors. So now coming to the vector projection. Suppose two vectors I am considering here. One vector is PQ, so starting from here ending at here, so this is having some direction along this side, and there is another vector called the RS, R and sorry S and R. So it is starting from here and moving towards this side, and this is the arrow, so it is called SR vector, and this is PR vector. So this is A vector and this is B vector, and the angle between the B and A is the theta. So here you can see the theta is the angle between both the vectors A and B. So if you draw a perpendicular from the head of the B vector to the tail to the perpendicular vector over the A vector, so it will basically intersect somewhere here. So this vector from the starting of the tail of the B vector to the perpendicular of this particular vector, so this is basically called the projection of B on A. So this is the notation, means B can be projected along the A direction also. So if you want to see the cross product, or let us say this scalar projection. So scalar product from the figure you can say this is the theta. So the cos theta will be PS, means base, divided by PR, that is hypotenuse. Okay, so PR upon PS upon PR, or we can write PS equal to PR times cos theta. So what is this PS? PS is nothing but this pink vector. Okay, so this is PS vector equal to PR. PR is nothing but V vector times cos theta. So you can say the projection of B vector along this side or along the vector A will be B vector times cos theta. So suppose you want to project one vector along the another vector, so you can simply write like the vector times cos theta. So theta is the angle between the given vector and the another vector along which you want to project the given vector. Okay. So and this PS equal to PR cos theta. So this you can write in terms of vector also, like PR vector dot cos theta. So PR is the b times cos theta, and this cos theta you can write like this: a dot b upon mod of a dot mod of b, just like the dot product of the two vectors. Suppose two vectors are there, and vector A and vector B both are connecting at a single point, or you can say the tail are common. Then the dot product of two vectors like vector A into vector B equal to mod of A into mod of B into cos theta. So from this relationship we can draw cos theta equal to A dot B upon mod of A mod of B. So same thing is written here. In place of cos theta, A dot B upon mod of A mod of B is written. Okay. So mod of B will be cancel out. So it will be A dot B divided by mod of A. So you can say the projection of B along the A will be the dot product of both the vectors divided by the magnitude of the another vector, which is A vector. Okay. So this is another relationship by which you can calculate the projection of one vector on the another vector. So you have to just take the dot product and divide it by the mod of another vector. Similarly, the vector projection of B on A means vector projection of B on A, we can write like this: projection of B in suffix, or it is mentioned as, it means projection of B on A, it is nothing but A dot B divided by mod of A, because you want to write direction also. So the direction of this projected vector will be along the direction of A, which means the A cap you can use. So A cap is the direction of the A vector. So that's what A cap is mentioned here. So vector A you can write the magnitude of vector A, unit vector, equal to vector A divided by mod of A. So mod of A will be multiplied. So A dot B divided by mod of A square times A vector. So this is another relationship by which we can calculate the projection of one vector on another vector equal to the dot product of both the vectors divided by mod of a vector along which you want to project and into the vector itself. Okay. So these are the relationships which we need to understand and we should keep in mind, because these relationships we will use in the subsequent processing. So now this is again this vector means there are number of ways to write the vector algebra, like if you want to write the vector B like this one, so this you can write like PS plus SR. See here that this tail and the heads are important, because the tail of B vector is here and head of B vector is here. So if you are coming starting from the tail and reaching to the head from another side, either this side or maybe multiple vectors if you are using. So this vector you can write PS vector plus SR vector, because here this is the path actually. So you can write PS vector plus SR vector is equal to PR vector. Okay. PR vector, or you can say simply the V vector. Or let us say there may be another situation, suppose S is somewhere here, let us say at this location some another letter is there, let us say X. So that time you can also write, and one vector you are connecting from P to X and then from X to S. So in that case you can write B vector equal to Px vector plus Xs vector plus Sr vector. So this is basically called the vector representation. Okay. Or you can say summation of a vector. So here in this basical equation only two sub vectors are involved, PS and SR, and another example which I gave, in that basically three vectors are involved. So these 2 and 3 are not restricted, you can write 100 of the vector, but the conditions should be satisfied, like if you writing this vector equal to one vector, that vector basically should start from here and somewhere there, another point, okay. And then from that point another vector should start, means tail should be there, and then that will reach to the another location, there it will basically end. Then from there another vector can start, means the tail of that can start, and that can reach to somewhere else. Then again from that point another vector can start, another vector can start, and finally they can reach to here. So you can say a single vector can be written as a sum of multiple vectors, okay. So you can say a single vector can be written as a sum of two or more than two vectors, provided they are satisfying a certain criteria, means they should start from the tail and end to the head, and again from another vector should start from the head of the previous vector and end somewhere else, then another next vector should start from the head of the previous vector and then end to somewhere else, okay. So that process should satisfy it, and then this in that way a single vector can be written as a sum of more than two vectors, okay. So that way we can write as this is the means B is the combination of these two vectors, okay. So now if you see, if you are coming to the InSAR processing, so here you can see, suppose we are investigating the land deformation or land surface motion from the InSAR analysis. So what we are getting? We are getting the displacement of a particular target along the radar line of sight. Suppose radar is here. Here you can see this is the ascending pass. So you know, in the ascending pass, satellite is moving from the south pole to the north pole. Not exactly from the south pole to north pole. It is basically starting slightly eastward of the south pole, and it is moving towards slightly westward of the north pole. So this is the trajectory. This is the trajectory of the ascending pass data. So you can say satellite is moving along this, okay. So what we are measuring, basically somewhere target is here, so this is called the line of sight. From here to the target, this direction is called the line of sight direction, or you can say the radar line of sight. So what we are measuring from the single pass data set, we are measuring either this target is moving towards the satellite, which is shown as a, you know, this arrow, means this target either is moving towards the satellite or moving away from the satellite in this direction. Means from single pass we are not able to investigate the horizontal or the vertical components of the displacement vector or the deformation vector of the target. We are only getting the deformation of the target along the radar line of sight, either towards the satellite or the away from the satellite. So if the motion or the you can say the motion or the displacement vector of this target is towards the satellite, so that displacement is denoted by the positive sign, or if the target is moving away from the satellite, means towards this side, then that displacement is denoted by the negative sign. So you can say whatever the displacement we are measuring from a single pass, either from the ascending pass or the descending pass, so if we are getting negative displacement, then we can say the target is moving away from the satellite. If we are getting positive displacement, then we can say the target is moving towards the satellite, okay. So this target is basically moving toward this side or this side, but in reality what is happening, in reality the motion may be in any of the direction. It is not necessary the target will move along this direction only. The target can move in any direction, either towards this direction, this direction, this direction, because this depends on the phenomena which is happening over a particular region. So landslide may be, you know, along the northward northeast direction or southeast direction, or in the three-dimensional way. So that motion vector may be in any direction randomly. It depends on the terrain, actually terrain characteristics, okay. So point is, whatever we are measuring from a single pass, that is not solving our purpose. Means by calculating only the line of sight displacement, we are not able to investigate what is the motion vector on the earth surface. So question is, we should basically investigate that real displacement vector. So how we can do it? So here I have shown here, basically here you can see this is the actual displacement vector I have just taken. So you can take somewhere else also. So this is the real displacement vector. You just don't be confused, like somewhere I have mentioned the land surface motion, or you can just assume the land surface motion vector. Motion vector means displacement vector, okay. And if you have the displacement vector, because displacement is a vector quantity, if you have displacement and if you have the time series displacement, you can calculate the velocity time series, okay. And if you have the velocity time series, then you can calculate the acceleration time series. So the displacement, velocity and the acceleration, these are the kinematic variables, which means you can understand the entire kinematics of that particular region, or you can say you are able to apply the Newton's law of motion, because Newton's law of motions are describing only the displacement, velocity and the acceleration, which because those Newton's law of motions are nothing but the relationship between displacement, velocity and the acceleration, which means if you have the displacement time series from here, then you are able to calculate the velocity and acceleration, and you are able to apply the Newton's law, or you can say you can understand the kinematics of that region, or you can say you can better understand whatever the process is happening over that region, what are the major causes of that particular region, and you can basically investigate that particular phenomena in detail if you have these three types of the parameters, okay. So main parameter here is the displacement vector, or you can say the motion vector simply. So here I am assuming, the actual displacement vector is along this particular direction, okay. So you can see from ascending pass InSAR investigations, we can calculate the line of sight displacement only, not this real displacement vector. So what we can do here, I am just now creating three dimensional frame here. So you can see this x axis is representing the east west direction, and north south direction is somewhere is like this. You just assume the three dimensional space. So this is the east west, then which is basically the horizontal plane. Same way in the horizontal plane itself, north south direction is there. So you can just assume like north south is somewhere here, okay. And then third axis is vertical axis, or you can say the perpendicular of this horizontal plane. So this is horizontal plane, and y is also, or north south is also on the horizontal plane, and then perpendicular of that one is the vertical plane. So now these three axes we are considering as a x, y and z. Let us say x direction is this x east west, y direction is along the north south, and z direction is along the up and down, okay. So what we can do, this real vector, real displacement vector can be expressed in terms of three components. One component of this displacement vector is along the east west direction, another component of this real vector is along the north south side direction, and the third component of this real displacement vector is along the up and down direction. So point is, initially we don't know what is the amount of this real displacement vector. So but our interest is to calculate this vector, real deformation vector or real displacement vector, okay. So we are not able to investigate it, we are investigating only the line of sight vector, which is not this real vector, okay. So as I mentioned, a vector can be written as like a1 x cap plus b1 y cap plus c1 z cap, okay, or a1 x cap plus a2 y cap plus a3 z cap. It means x, y and z components are written there. So point here is, if you want to investigate this real displacement vector, it means you can investigate those three components separately, and then you can combine all those three components in the form of that vector, like a1 x1 x cap plus a2 x y cap plus a3 z cap. Then it means if you know three components, it means you know this vector. The knowledge of this vector is basically the knowledge of its component only. So but overall interest is to investigate this real vector. So this is not available. So what we are doing, basically we are trying to calculate this component. Its component means east west component, north south component and up and down component. If we component we know, then we can know this vector, okay. Then point is, those component itself we don't know. So how to get those components? So point is, those components, or you can say this real vector we can project along the line of sight vector. Point is, we are trying to correlate this real deformation vector with the line of sight vector, so that some relationship we will have between the real deformation vector and the line of sight vector which we are getting from the a single pass, either from the ascending or the descending pass. Then some relationship we will get it, and we will try to solve that relationship, and from that relationship we will be able to find out the real displacement vector. So here you can, now more thing I can just explain here. Suppose this is the 3-dimensional real vector, and if we decompose, okay, then its one component is along the this pink line. You can say just like projection of this one along the x direction. So the projection of this one will be this, which is pink dotted line. Another component of this one will be along this direction, which is up and down direction. So you can say this one component is along the x direction, another component is along downward direction, another component will be along the north south direction. That is not visible here in this particular figure. So point is, if vector is here, then we can decompose along this direction, and the north south direction also. Okay. And if this motion is basically moving towards this side, then again it can be decomposed like upward direction or the downward direction. So you can say towards the west direction, towards the vertically up direction. So my point is, if this motion is moving away from this, then this is the vector, its component is this, and if it is towards the satellite, then its component is this. And it means by decomposing this along this or this, and decomposition of this along this or this, we can calculate the component of this motion vector along the upward direction or the horizontal direction, and from those components we can calculate the real vector. Okay. So we will try to establish the relationship between the line of sight motion towards the satellite, so away from the satellite, and the different components of the motion vectors. Okay. So here you can say this is the scenario if we are acquiring the data set in the ascending pass. This is the theta incidence angle. Okay. And the same situation we can just assume in the descending pass. So descending pass is basically satellite is moving from the north pole to the south pole, not exactly from the north pole to south pole, it is basically slightly eastward of the north pole to slightly westward of the south pole it is moving. Okay. So again, if the target is moving towards the satellite or away from the satellite. So if it away from the satellite, then it can be decomposed along this direction and along this direction. If it is moving towards the satellite, then its component along the east direction or along the upward direction, or another component is also along the northern side. Okay. So from the line of sight displacement, we can establish a relationship between the line of sight and these components, and from these components of the deformation vector we can draw this real deformation vector, and this is basically called the satellite incidence angle. Okay. So now we will try to understand basically how we can correlate or establish a relationship between the line of sight deformation with the different components of the real deformation vector. Okay. Here I have mentioned like the satellite heading is also there, so that is denoted by alpha h. Satellite heading is nothing but the angle of this satellite trajectory. This is called the satellite trajectory with the north direction. So north direction here it is mentioned like in the horizontal direction. So how much angle it is making with the north, so that is called the satellite heading. Okay. And another angle is there, that is called the azimuth look direction, generally denoted by mu. So mu is related with the satellite heading itself. So mu equal to satellite heading minus 3 pi by 2 means 270 degrees. So this is applicable for both ascending as well as the descending passes. So you can say the azimuth look angle for ascending data is equal to the satellite heading of the ascending minus 270 degree, or azimuth look direction from the descending, again satellite heading in the descending minus 270 degree. But this is applicable for the right looking radars, but for these left looking radars, the relationship will be alpha h minus pi by 2. So here it is important to note that this relationship is true for right looking radars. So here you can see now both ascending and the descending passes are combined together, or you can say the coupled together, so that the real deformation vector can be written in terms of line of sight displacement vectors, means line of sight displacement from the ascending and the descending data set. So here you can see this is the line of sight displacement vector from any of the pass, either descending or the ascending, and then P is the projection vector and D is basically the real deformation vector. So you can say the real deformation vector can be projected along the line of sight vector with the projection vector is this one, which is minus P. So minus is written because the real vector is somewhere here and line of sight is just opposite of that, that's why the negative sign is mentioned over here. So now if you write in detail, so you can see this line of sight displacement, which is DLOS, equal to this minus P vector is nothing but these three components. So here you can say minus sin theta sin mu, this is the first component of this projection vector, and this is the second component minus sin theta cos mu, and this is the third component of this projection vector, which is cos theta. What is theta? Theta is the incidence angle, mu is the azimuth look direction. Okay, so azimuth look direction is related with the satellite heading, which we have already seen in the previous slide. And what is this? This is nothing but D. D is having three components, means displacement along the EW means east west direction, and D NS means north south direction, and D up and down means vertically upward or vertically downward direction. So these are the three components of the actual, or you can say the real displacement vector, and these are the three components of the projection vector, and this is the line of sight vector. Okay, so in this relationship, this is only single equation, but you just go in detail, because this displacement line of sight displacement you can get from any of the pass, either from the ascending or from the descending pass. Theta is known for the satellite, or incidence angle is for the all the images, and mu is related with the satellite heading, and satellite heading is known for both the passes, ascending or descending. It means this P vector from here to here, it is also known. So just keep in mind, this we have drawn from the InSAR application. So this is known, and these three components are known, and what is unknown? This is unknown. This east west component of the displacement vector is unknown, this is also unknown, this is also unknown, or you can say this is our interest, means we want to investigate these three components. So point here is, this we have only one equation, this is one equation, but this equation having three unknowns. So you just go back to the linear equation. Suppose you have only one equation with three unknowns, so number of unknowns are more, number of equations are less, then you cannot solve that equation. Okay, in fact infinite many solutions are there. For example, y equal to mx plus c, if I am writing, okay, so unknowns are basically m and c, means two unknowns are there, but single equation is there, y equal to mx plus c, this is linear equation. Let us say m and c are unknown and x and y are known. Okay, so this is single equation but two unknowns, so two unknowns cannot be calculated from the single equation. So what can be done? We can assume different values of x, then different values of y can be calculated. But for the assumption purpose, so many values of x you can assume, it means so many values of y you will get. Okay, so from this equation we can say infinite many solutions are possible, means if number of equations are less than number of unknowns, then for that particular system we have infinite many solutions. But suppose if you have two linear equations and two unknowns are there, it means number of equations and number of unknowns are same, it means you can get the unique solution. Unique solution means only single value of both the unknowns. So there is another situation also, if number of equations are more than number of unknowns, means you have the 10 equations and 2 unknowns, means number of equations are more and number of unknowns are less. So that is in general the situation of the no solution. Just remind the type of the solutions of the linear systems. If number of equations and number of unknowns are same, it means that is the situation for the unique solution. If number of equation are less than number of unknowns, then it is the situation for infinite many solutions. And if number of equations are more than number of unknowns, it means that is the situation for the no solution. Okay. So what we are getting here, one equation 3 unknowns, means number of equations are less than number of unknowns. It means this is a situation for infinite many solutions, means so many solutions we can get, but we are not thinking, for basically that is not possible, means whatever the deformation is happening, that is a real deformation. It means only single value is there. You cannot think like so many types of the deformations are happening. Okay. So we are not interested in the infinite many solutions. It means we are interested only in the unique solution. But theoretically from this equation it is not possible, because single equation is there and 3 unknowns are there. So what we can do, we are trying to combine both the equation, because the same equation, this equation we can write for the ascending path also, and the same equation we can write for the descending path also. So in that case we will have the 2 equations. So those 2 equations are written here, you can see. Now it is written in terms of velocity, but you can write in terms of displacement also. So like displacement, line of sight displacement from the ascending path, the equation is the same equation, sin theta sin mu, sin theta cos mu, and cos theta. And theta means theta a means ascending, mu means mu a, which is ascending, a denotes for the ascending path, and these vectors are there. And from the line of sight from the descending path, again it is written, and same components are there, because real displacement vector having the same component, it is not going to change. You cannot write from ascending path we are writing different component of displacement vector, and from ascending path again different vector. So that is not possible. Only single means components of this actual or the real displacement vector are unique. That's what we are not going to change. So B or displacement EW, NS, and up and down. So now you have 2 equations in this equation. See, this line of sight displacement from the ascending path is known from the INSAR investigations. Line of sight displacement from the descending path, it is known from the INSAR investigations. Theta a means incidence angle from the ascending path, it is known. Mu a means azimuth look angle from the ascending path, which is known. Incidence angle from the descending path is known. Mu d azimuth look angle from the descending path, it is known. It means all these components are known in the projection vectors. So these are known, these are known. What is unknown? These 3 components of the actual displacement vector. So now what we are getting here, 2 equations but 3 unknowns. So again it is not possible. Means if you have number of, again we are having number of equations less than number of unknowns. 3 unknowns, 2 equations, which is not possible. Now we cannot write the third equation, because up to here we have basically options, means one equation we can write from the ascending path, another from the descending path. Now we don't have any third path. Satellite is having only 2 passes, ascending or the descending. No third pass is there. It means no third equation can be written here. So what we can do, we have to basically assume something, or we have to ignore something from these two equations. So what we can do, out of these 3 components, one component we can drop, so that 2 components will be remaining there and 2 equations are there. Then we can uniquely we can solve this particular equation, and we can get unique value of each component. Okay. So which component we are going to drop? So again we have to think which component is good to drop, along the east-west direction or north-south or up and down. So by this practical example of the satellite geometry, if you drop the north-south component, then it is justified. Justified in the sense this VNS denotes the displacement along the north-south direction, and north south direction means satellite also is moving from the north pole to south pole or south pole to north pole, or you can say along the north south direction satellite is moving. So satellite is moving along the north south direction, it means whatever we are investigating along the north south displacement, that cannot be investigated with great accuracy. Okay. So if this the displacement in this direction cannot be measured with the great accuracy, so it is better to ignore this component. So this north south component can be ignored, or you can say left. So you can say if this is ignored, it means these components, because this first component is corresponding to this one, second is corresponding to this one, and third one is corresponding to this one. So if we are ignoring this, it means we have to ignore these things also. So by after ignorance, just a minute, yeah मैं आ रहा हूँ थोड़ी देर, हाँ हाँ बोलिए. ठीक ठीक ठीक, ओके ओके, गुड गुड. So so we are now ignoring the VNS, or you can say DNS, there is a displacement along the north south. So these two components are ignored. So now resultant equation is like this. So these components are known, these are these two components, these are ignored, and only the third row is written here. So now only two components are left. So now you see two equations are there, two unknowns are there. So these two equations and two unknowns can be solved uniquely, and unique solution we will get. So you can say one value of east west direction or east west displacement, and one value for the up and down component can be calculated from this relationship. So the east west displacement is called the horizontal component of the displacement, and up and down component is called the vertical component of the displacement vector. So now what is basically we are not getting from this coupling of the ascending and descending data sets, that is north south component. So keep in mind, whenever we are investigating the deformation from the InSAR analysis, and by coupling both the ascending and descending data set, we are able to get only east west displacement and the up and down displacement. No north south component we are able to calculate because of this theoretical and the practical limitation. Theoretical means these equations tells us if more number of unknowns are there, then equations are less, then we cannot investigate all those unknowns. And practical limitation is there. For satellites we don't have more than two passes, only two passes are there. So practical as well as the theoretical combination if you considering, then we are ignoring something, and within that assumption or ignorance, the final equation is this, and which basically tells us we are able to calculate the east west horizontal component of the displacement vector, and up and down, that is vertical component of the displacement vector. So you can say we are able to calculate only two dimensional displacement vector of the deformation, not the three dimensional deformation. Okay. So here you can say east west is the x component, up and down is the z component. So that actual deformation vector you can write like actual vector equal to displacement along the east west into unit vector along the east west direction plus up and down displacement vector component into unit vector along the up and down direction, which is you can consider as z direction also. So whatever you like, you can just consider it. Okay. So now try to understand the limitations of the InSAR. Okay. We are not able to calculate the three dimensional deformation vector, but yes, there may be certain simplifications in this analysis. I am just going back to one slide. Here you can see, suppose you are calculating only from the ascending pass data set. So you have basically line of sight vector along towards the satellite or the away from the satellite, only one you will get it. Okay. So suppose in your area only land subsidence is happening, only land subsidence, you are sure like horizontal motion is not happening, only vertical motion is happening in your area, then directly you can use the line of sight vector of the single pass data along the vertical component or the downward component. Okay. Suppose line of sight displacement is negative, it means this vector is towards this side. If you are decomposing, then it is basically towards this side. So that is called the subsidence. And if it is positive, it means the component of this one will be this side, that is upliftment. So both the things you can investigate from the single pass, but for that you should be sure in your study area only motion is in the vertical direction, not in both the directions. So in that case you can say only single pass data is sufficient to calculate the vertical component. Okay. So and if you are sure the motion is not only in one plane or one direction, it is all three direction, then in all three direction it is not possible, only two direction you can calculate, east west and up and down. So that is only possible by combining the outputs or line of sight outputs of the both the ascending and descending passes. Okay. Then there is another problem in applying this particular equations, whatever is shown here. So theoretically it is seems fine, but if you apply practically, then again there are some difficulties. Difficulties in the sense, you can see here, suppose this is representing the line of sight displacement from the ascending pass. Okay. So tomorrow we will discuss some advanced techniques of interferometry. So those outputs are basically point outputs. So suppose if you are ascending the processing the ascending data sets, then the point distribution is like this one, means point output is like this one, and the same area you are investigating using the descending pass, then let us say the points are like this one. Okay. So you can see the output from the descending pass is different from the ascending pass. So if these are different, it means you cannot apply this equation directly. Means in order to apply this equation, means this equation can be applied over the single points, or you can say the common points. Means over the common point you should have the line of sight velocity from the ascending and line of sight velocity from the descending over the common point, then only you can apply this equation. And in this figures what you can see, suppose I am talking about over this particular pixel. So over this pixel line of sight velocity from ascending pass is there, but from descending pass is not there. It means you are not able to apply those equations. So what we can do, we are basically applying some resampling techniques, so that we are getting what we are doing basically, if some common grid we are assuming, and over this common grid and using these distribution we are filling the value over each and every pixel. So by filling each and every pixel, so this types of the information we will get it. Okay. So these are basically the line of sight velocity from the ascending pass over different pixels, and same grid if it is resampled using this data, then we are getting this types of the information, or you can say over each and every pixel we are getting the information. Now we can apply those equations. Which equations? Whatever we previous these two equations. So now you see over each and every pixel, suppose if we are talking about over this pixel, it means over this pixel line of sight velocity from ascending data set is there, and over this pixel line of sight velocity from descending data set is also available. It means over the common pixel, this and this is the same pixel. It means over the common pixel the displacement from both the passes are available. It means you are able to apply these equations, and if you are applying these equations, then you can say you can calculate the east west component and the up and down component. Means what is this east west? By combining ascending as well as the descending, from up and down, from ascending as well as the descending, applying those equations, previous equations. Okay. So that way you can calculate the horizontal and the vertical components. So don't think these equations are sufficient. These equations are not sufficient. These things you have to basically apply. Means whatever the output from the ascending and the descending data sets are there, those you have to interpolate over the common grids, and over the common grid both the values you will have, then you are free to apply those equations, and finally you will get the horizontal and the vertical displacement vectors. This is another slide which is again showing the direction of azimuth look and the trajectory. As I mentioned in the previous slides also, suppose a satellite pass you want to see in the ascending pass, so it is moving from slightly eastward of the south pole to the westward of the north pole. So this is the trajectory, that is called the satellite trajectory. Perpendicular of this one is called the azimuth look direction, because this is right looking radar. So the angle from the north direction, this is called the azimuth look direction. Okay, if you are measuring the angle clockwise direction, then it is called basically the positive angle. If this angle you are measuring like anti-clockwise, then you can assume as a negative angle. Okay, so here you can see in the ascending this is ascending configuration. So in ascending pass, this angle is called basically satellite heading. So you can see the angle between the satellite trajectory with the north side is called the satellite heading, means this angle is called the satellite heading. And the angle between the look direction, azimuth look direction from the north direction, this angle is called azimuth look angle. Okay, so keep in mind, if you are mentioning in the positive sign, then you are basically measuring this angle. Okay, another way of measuring this angle is like if you are measuring anti-clockwise, so from angle from here to here, this is also called the azimuth look direction. So my point here is the azimuth look angle you can write with plus sign or the minus sign also. So if you are writing with plus sign, it means you have to simply measure the angle from here to here, and if you are measuring with negative sign, it means you should measure the angle from this here, means north side to anti-clockwise up to here. Okay, so now you can have some basic idea what should be the azimuth look angle in the ascending pass or the satellite heading in the ascending pass. So satellite heading, if you are measuring in negative sign, it means this is simply angle from here to here. So this is around 15 degree, minus 15 degree. So satellite heading in the ascending pass is around minus 15 degree. Okay, or azimuth look angle is around, this is total is from here to here it is 90, this is 15 if you minus, so it is 75. Okay, so this angle is plus 75, or you can say this is minus 285, means this, if this is 75, so the angle from here to here it will be 360 minus 75, which will be around minus 285. So you can write azimuth angle as a minus 285 degree or plus 75 degree. Similarly, you can write for the satellite heading also minus 15 degree or plus this side 345 degree. So satellite heading you can also write minus 15 degree or plus 345 degree. So these are the ways to write satellite heading and the azimuth look direction. The same approach you can apply for the descending pass also, because the descending trajectory is like this and azimuth look direction is like this. So the angle from north to azimuth, this is plus sign, or you can write this one as a negative sign, or the angle from here to here it is plus sign, or from here to here it is negative sign. So accordingly you can basically decide what should be the angle. But yes, in the descending pass, this angle satellite heading is around minus 165 or 170 degree. Minus means from here to here it is minus 165 degree. So accordingly other angles you can calculate. Okay, this is the relationship for the right looking radar. The mu equal to satellite heading minus 3 pi by 2, for left looking heading minus 90 degree. So this is the 3-dimensional views. Okay, and this is nothing but for the pure 1-dimensional motion, like motion along the slope. You can write the line of sight displacement divided by lambda v, and lambda v is written in terms of these 3 angles. So these are the incidence angle, slope of the terrain, aspect of the terrain, and the phi. So you can say the displacement along the slope is particularly in case of landslide, you can also calculate using this particular equations. So thank you so much. If you have any questions